a circuit used, the LDR is not shown. Complete figure 6.1 by drawing the circuit symbol for an LDR between the points P and Q. So we need to place the LDR symbol, should be an easy one, over here. This one followed by 2 arrows like this. So this is a symbol for the LDR as given in the learning objectives of O-level physics. So this one was for 1 mark. Explain how the voltmeter reading changes as the amount of light falling on the LDR increases. Now this one is, you have to be careful with it, because the effect of changing the light is not going to affect the voltage directly, because the voltmeter is not connected across LDR. This is the first thing that you need to realize. Whatever the effect of voltage is going to be on the LDR has nothing directly to do with the voltage, because the voltmeter is not connected with the LDR. Rather, the voltmeter is connected over here with the other one resistor. So let's see what happens with the voltmeter reading on the LDR as the light increases. So in light, when the light increases, what happens is the resistance of the LDR drops, all right, in the bright light. Or as the intensity or as the amount of light increases, the resistance of the LDR drops. This is something that we studied in the theory. Then if the resistance has dropped, it'll be getting smaller amount of voltage. We also studied this relation, since V equals I times R. And if you have low resistance, then you'll be getting low voltage. No potential difference would be there across the LDR. So if LDR is going to get less share of voltage, then more share of voltage would be available for the other resistor, this one, and hence the reading on the voltmeter would be increased. So as amount of light increases, or intensity, whatever you want to write, amount increases, voltmeter reading, the potential difference across LDR decreases, due to reduced resistance. Hence the voltage, or hence the voltmeter reading, because the voltmeter is not connected across the LDR, it is connected across the other resistance which is in series. So that resistance would be left with a bigger share of the voltage comparatively. So the voltage reading on the voltmeter would be increased. Hence voltmeter reading increases. All right, had the question been in the bright light, or as the amount of light increases, what happens to the voltage of the LDR? I mean, think about it. The voltmeter is not connected over here. So just for instance, I'm going to disconnect the voltmeter from here. Let's say there's no voltmeter over here. And matter of fact, I'm going to connect a voltmeter over here with the LDR. in this case, the answer would have been, as the amount of light increases, the resistance of the LDR decreases, and hence the voltage across the voltmeter reading would also decrease, because voltmeter is directly connected to LDR. Whatever happens to the voltage of LDR, that would be the answer for the voltmeter reading. But since in the question, the voltmeter is not connected to the LDR, rather it's connected to the other resistance. So the effect would be the other way around, opposite effect. We clear with this one? All right, moving on to the next one. This one is of 2 marks and followed by the other one of 2 marks once again. Figure 6.1 shows part of the circuit containing 3 resistors. And if you have to read the circuit, then the circuit is read as 2 resistors connected in parallel, these two, followed by a resistor connected in series with those parallel resistors. And the value of current in the 4 ohm resistor is 2.4 ampere. All right, it's given over here, 2.4 amperes. Show that the current in the 5 ohm resistor is 1.9. You need to find the current in this one resistor. All right, so the very famous equation from this chapter, once again, V equals IR. This is F equals to MA for this one chapter. And we can rearrange it for finding the value of I, and I would be equal to V over R. Now the thing is, we don't have any problem with inserting the values. We can get the values from the circuit itself. The value of R is this one, 5 ohm. So we can, instead of R, we can write 5. That's the value of resistance. Then the question is, what is the voltage across this 5 ohm resistor? It's not given directly. We are not provided with the value of voltage across the 5 ohm resistor. So how do we apply this formula? Now the thing is, this is where we apply some of the properties of series and parallel circuits. One of the property of parallel circuit was that the voltage across all the components remains the same. So if somehow we are able to find the voltage across this one resistor, that would be same as the voltage across the lower one, because both of them are connected in parallel. Now, can we find the voltage across the 4 ohm resistor? The answer is yes, we can, because voltage, once again, the formula we have V equals to IR, but then you realize that you have the value of current and you also have the value for the resistance. So that'll be 2.4 times 4.0. And what do we get? You can just hit it on the calculator. So 9.6 volts is the voltage across this one, and that'll be same as the voltage across 5 ohm. Reason, both connected in parallel. You see, properties are being used indirectly. They don't, for the most part, they don't ask you, is the voltage same in parallel circuit? And then you're provided with 2 options, yes, no. No, you don't get questions like these. You get the questions in which you have to relate or recall those properties and use them indirectly. So the voltage across this one would also be 9.6 volts. So 9.6 you can write over here. Then you can hit it on the calculator, and what do we get? 1.92 into SF, we get 1.9, which is the same as we need to calculate. Matter of fact, we had to show. So right now, I also have the voltage across, the current across passing through the lower resistor, which is 1.9 ampere. and I can raise off this one for a while. Yeah, I have the current in the 4 ohm resistor 2.4. I have the current in the 5 ohm resistor as 1.9. All right, moving on to the next part. Calculate the potential difference P dot D between the points X and Y. In order to find the potential difference between points X and Y, all you need to have is the total current that is passing between these 2 points and the total resistance that is there between these 2 points. That's it. You need 2 things once again, because the formula for the potential difference is V equals to IR. All you gotta do is you need to be having 2 things. One of them, the value of current, means the total current between the point X and Y. And the value of resistance means the total resistance between the point X and Y. So let us find both of the things. You see, finding the total current between these 2 points is very easy. I mean, think about it. There was some current coming from here, the total current. It was coming from here, from 6 ohm resistor. It was just moving on to the right side. And all of a sudden, that current parted ways. Out of that current, 2.4 ampere went through the upper side and 1.9 ampere went from the lower side. Then the question is, how much current was coming in the first place that was then divided? The answer is we can add both of them, 2.4 and 1.9. I mean, this is the division, and the total current would be 1.9 plus 2.4. 4.4 and 4.3. 4.3 amperes. This is the total current that is passing between the point X and Y. I mean, and if you analyze this one, 4.3 was coming from here, 4.3, 4.3. At this point, it was divided into 2 parts. But as it reaches this point, that again combines and the total current would be 4.3 once again. Anyway, then the question is, how do we find the total resistance of the circuit between the points X and Y? Between the points X and Y, the resistors are connected in compound connection. Compound means both series and parallel. So we sort out this one first, the parallel combination. I have 2 resistors. One of them is 4 ohm, the other one is 5 ohm. They are connected in parallel combination. What would be the total resistance of this one unit? So the total resistance for these resistors connected in parallel, the shortcut is, I'm going to use the question that we have is product. A student connects 4.0 into 5 thermistor X divided by at this stage you must be familiar with the thermistor. Matter of fact, we studied that in the previous 2 lessons, all the electrical devices. So you have a thermistor divided by 9, and this is a symbol for the thermistor, and the total resistor only for that unit is, what do we get from here? What do we call this one? A battery. All right, make sure you are familiar with all the symbols. This one is for the cell, once again, a single cell. The one for the battery is already given. All right, so 2.2 ohm is for the power supply. Only the resistance of this part. These symbols are different. But you see, if they ask you to draw this whole part, if you consider it as a single unit, all of them, all right, just consider it as a single unit. This single unit is connected with this one in the series. Symbols have to be used as how do we find the total resistance in series? We simply add them by the O-level physics. So the total resistance between the points X and Y, these two are connected in parallel, as you can see over here. these two components are connected in parallel between the points. EMF of the
X
battery
and Y,
is E.
that
would be 2.2. What is EMF? The definition
right, 2.2
has to be
from this
memorized.
unit,
They ask
and
you
6
for
from
1 or
this
2
unit.
marks.
plus 6.
And the keywords in the
And what do we
definition
get?
are,
We get 8 point.
the work done or the energy supplied by the
We
unit
do
charge
have the
passing
value
through a
of
complete
total
circuit.
resistance, and we
Complete
do have the
circuit,
value of
work
total
done on the
current.
charge.
It would be very easy
These are
to
the
find the
keywords.
value of potential
So
difference.
EMF of the battery is
So
E.
in this situation,
Current
V equals, again you use the formula
in the
IR.
component X,
Now
or
we
current
have
in
the
the
value of the
thermistor
total current,
is
which is
I
4.3,
amperes. Right? They haven't calculated it. It's just given as a general value, I amperes
times the total resistance.
So this is the thermistor,
which was
I can write
8.2.
over here as well.
Then we hit it on the calculator.
And what
And
do
the
we
other
get
one is a
here?
normal resistor,
Fixed resistor. The resistance of Y is greater than the resistance of the X.
35.26. I'm going to write 35.
Alright, this
as
might
two
be
significant
helpful
figures.
in the parts that we have to solve
So that would
afterwards.
be
So
the voltage
resistance of
across
Y is
between
greater
the points
than the
X and
resistance
Y,
of,
or the potential
X.
difference between the
the
points
resistance
and
of
Y.
X is small.
So you realize,
and the
you
resistance
first
of
need
Y
to write down the
is
formula.
greater.
Then you need to find the total current
So this is
by
the information
adding these
that we
two
have
currents,
so far.
and then you need to find the total resistance.
Tick 2
And
boxes.
for that one, you need to sort out this parallel
One to show the
combination,
correct statement
and then
about the
the
potential
series
difference
combination.
Y, and the other
So
to show the
plenty of
correct statement
concepts
about the
are
current
being
in Y.
tested in the same
So you
question,
have to
in
answer
a single
for
question.
potential difference in Y and the current in Y. Potential difference, in simple words, once again, the voltage. The potential difference across Y, the first one says is less than E, means the less than the voltage of the battery. Second one says is equal to E, equal to the voltage of the battery, or the third one says greater than the voltage of the battery. Let's check out the circuit. Component Y is connected parallel with the thermistor directly to the battery. And we studied that in the theory portion, that when the components are connected directly, connected in parallel directly to the source, to the battery, to the power supply, the voltage across them, or the potential difference across them, equals to the EMF of that battery, or EMF of that power supply, or EMF of the cell. And in this case, that condition is being satisfied. So the voltage or the potential difference across Y is equal to the EMF of the battery, the middle one. Then we have to draw for the information, mark for the information about the current in Y. Now think about it. So the total current coming from the battery reaches this point, and exactly at this point the current has two possible paths. Either the current can go from X, some of the current would go from X, and some of the current would go from Y. What you have to figure out is through which path more of the current would be passing, and the answer is the path with the less resistance. So in through the component Y, say it is having more resistance, so less current would be passing through this one, because current always want to follow through the easier path. So less current is passing through the component Y. All right, so we can, current is less than I. Or I mean, yeah. Anyway, we have to compare with I. I was the current passing through the X, then the current in the component Y would be less than that. Might be 0.9 times I, 0.8 times I. It would be less than I. If I is 2 amperes, then the current through the component Y might be 1.7, 1.6, 1 ampere, depending on the resistance. But anyway, it would be less than that one. We clear so far? All right, then we have the next one. The student connects thermistor in series with the resistor and the battery of the EMF 6 volts as shown in figure 5.2. In the circuit at room temperature, the resistance of thermistor X is 600. This one is 600 ohm, the resistance. And the current in the thermistor is 0.0020 ampere. That much current is there passing through the thermistor. Calculate the power produced in the thermistor. And this one is of 2 marks. Calculate the power produced in the thermistor. And yeah, that's it. So for power, I'm going to write the formulas that we studied. P equals to, one of them was V times I. One of them was P equals V square over R. And one of them was P equals I squared times R. Which one is the most compatible? I mean, all of them you can use indirectly, but which one can be used directly? Which one of these three? Yeah, very good. P equals to I squared times R. We can use it directly. So I squared would be 0.0020, the square of it, and we gotta multiply it by the resistance of the thermistor, which is 600 ohm. Then we hit it on the calculator and we find out the answer. Sorry, what again? All right, 2.4 into 10 to the power negative 3 with the unit of watts. All right, electrical power or any kind of power, the unit is watts or joule second, but we write watts. So this is the power produced in the thermistor. Could have used all the formulas, but for those one we need to do some indirect calculation. First we needed to calculate the voltage. All right, then in the next part we need to calculate the resistance of Y. This one, its resistance, I mean the resistance of the first one is thermistor is 600 ohm, but what is the resistance of the fixed resistor? Let us write down, let us look at the tools that we have. And like I said, the most famous one is V equals to I times R. And if you rearrange it for the value of R, then R would be V over I. For the resistance, and you see this one is of 3 marks. So means it's obvious that you have to do some indirect calculations. There won't be a single equation that is going to give you the value of the resistance of Y. Matter of fact, you'll be required to use a couple of equations to reach up to the value of resistance. So what do we do is, one of these two things is given directly. I mean, think about it, the value of current. How much current? I mean, we know the value of current passing through the resistor, through the thermistor, which is 0.0020 ampere. But what is the value of the current that is passing through the resistor Y? Very good. It's just the same, because these two are connected in a straight line that we call they are connected in series. All right, so we're good with that. We're good with the current. But then the thing is, what is the voltage across the component Y? All right, so in order to find the voltage, we have the formula V equals IR. I mean, this should be the first thing you're writing down, V equals to IR. Then the problem is we do have the value of current, but we don't have the value of resistance. I mean, matter of fact, this is a thing that we were calculating. So we can't find the voltage using this formula. We have to find the voltage using the properties of the circuits. So in the equation, when more than one thing is missing, then you have to use the properties in the questions of the circuits. Now the properties for the series circuit is the total voltage of the battery. One of the property was the total voltage of the battery equals to the sum of voltage over here plus the sum of voltage over here if you have two components, V1 plus V2. I mean, if you have 6 volts coming from the battery, out of this 6 volt, some of the voltage would be given to this one and some of the voltage would be dropped across the second one. But if you add the voltage across these two components, you get 6 volt back again. Now, V2 needs to be calculated. V2 needs to be calculated. Do we have all the other values? Yeah, indirectly we do have. Indirectly we do have all the other values. I mean, yeah, we were at this thing, calculating the resistance of Y. The Y is the fixed resistor, right? So we have to use some of the properties of the circuit. So the total voltage of the battery, which is the 6 volt, a portion of that voltage is to be dropped over here and the remaining portion would be given to the component Y. How much voltage is going to be dropped across the component X? We can find it out once again using the famous equation V equals IR, or the expression for the Ohm's law. So this is V equals, the value of phi would be 0.0020 times 600, right? And then we can know the voltage across the component X, and you hit it on the calculator and what do we get? So out of these 6 volts, 1.2 is being supplied to the component X. So we write 1.2 over here plus V2, and V2 would be the difference of these two, 6 minus 1.2. So that'll be 5.2 minus 4.8 volts, and you write 4.8 volts over here. You hit it on the calculator once again. Should be more than 600 at least. Hmm. 4.8 divided by this. So I'm going to just all right. 2400, right? 2400. This is the resistance with the unit of ohm. And the solution is there on the diagram. All right, then we have the next part of 2 marks. The thermistor is now cooled. The temperature decreases. Explain why this causes the potential difference across Y to decrease. Once again, the question is not, you not ask for the direct relation between the thermistor and the potential difference, because they are decreasing the temperature of the thermistor, but they are asking for the potential difference across y, across the other component. So what happens for the voltage across the thermistor itself? So if the temperature decreases for the thermistor, if the temperature decreases, I'm writing over here, the temperature decreases, due to that, the decrease in temperature, the resistance would be increased, the resistance of the thermistor would be increased. Thermistor behaves opposite to the conductors. For the conductor, you decrease the temperature, the resistance also decreases, but for the thermistor it's the other way around. The resistance increases, and if the resistance increases, the voltage drop across the thermistor would also be increased, and thermistor was a component X, so Vf would be increased, Vx would be increased. And what happens is your battery is going to supply more voltage to the thermistor this time. The thermistor would be getting more than, there would be more than 1.2 volts across the thermistor, and the remaining voltage would be across the component Y. So this time, since the component X is now getting a higher potential difference compared to the previous case, so the component Y would be left with less potential difference compared to its previous value. So then what you write is, since component X, the thermistor, has more potential difference than before, so component Y will be left with less potential difference compared to the previous case. Or you could have simply written, so the potential difference across Y would be decreased. Compared to its previous value.